ahead and just jump right in to today's lecture. Okay. So section 12.4 is all about this introduction to polynomials. You've probably heard this word polynomial before. Maybe you didn't know what it meant. Maybe you've heard a reference to them in pop culture. But fundamentally, a polynomial is an algebraic expression. So polynomials are algebraic expressions that have terms. And remember, term is just a word that refers to either numbers or variables, or both, that are combined using, I'm just going to say, arithmetic operators. Okay, well, that's a lot of fancy language to describe what a polynomial is. But fundamentally, what I mean by this is that polynomials are expressions that have numbers and variables that are combined using arithmetic operators. And what I mean by arithmetic operators is specifically they're going to be combined with addition, multiplication, subtraction, right? Those are the fundamental ones. Operators that we use, or operations, is probably a more familiar way of hearing it. But we'll start off with a simple kind of polynomial called a monomial. Here I find that the word polynomial is useful to break it down into its etymology. So polynomial comes from the Greek poly, which means many, and nomial comes from a Latin root which refers to names. Like nombre in Spanish means name, or nom in French means name. Polynomials, you can think of them as being many names or many terms. Okay, but the fundamentally, the simplest kind of a polynomial that we're going to learn about here is the kind of small polynomial on which all the rest of the polynomials are built on, and those are called monomials. Monomial is a polynomial with only a single term. Some examples of a monomial would be something like let's say x to the third power. Or 3x squared. Or simply x. Okay. So what I mean by this is you can think about each of these expressions here as being some sort of variable expression with some operator like an exponent, or a number times a variable with an exponent, or just a variable by itself. But fundamentally, this would just be a single term. This would be a single term. And this would be a single term. So individually, these are monomials. There's only one term. So what we want to do is then introduce some additional vocabulary. So I'm going to say that the degree of a monomial refers to its exponent, or the exponent that exists on the variable. So here, for this first example, we would say that this is a monomial of degree 3. So x to the third would be a monomial of degree 3. Whereas 3x squared, again, degree refers to its exponent, the exponent that's on the variable. So we would say that this is a monomial of degree 2. But what about this guy here? So this example doesn't seem to have an exponent, but you have to remember that in the example x, just this term, that when we learned about exponents the other day, we said that x to the first power is just x. So when you don't see an exponent here, it's understood that the exponent is 1. So we would say that the expression just x is a monomial of degree 1. But now I have a question for you guys. All of those monomials that we just showed had some sort of variable component. What about the constant term? So is the number, let me just pick a number, 5, a monomial? What do you guys think? Just the number 5 by itself. Well, if we think about the definition, right, of what a polynomial is, it's an algebraic expression that can have numbers or variables that are combined using arithmetic operators, right? Or it could just be a polynomial with only a single term, right? But again, terms means either a number or a variable. So keeping that in mind, it should be pretty clear, you know, if we use that definition exactly as it said it could be a number or a variable, or both, well then 5 should be considered a polynomial. So even though we think of it as just being a number by itself, we can consider 5 to be a monomial because it's only a single term. And we're going to call this a monomial. Any number by itself will be a monomial of degree 0. Now, the reason why we can call it degree 0 monomial is because of what we learned last time about exponents. So follow me, if you will, on this logical journey. Think about 5, the number. Is it not true that 5 is equal to 5 times 1? Well, that's definitely true. Okay. But last time, we said that if we had a variable raised to a 0 exponent, that is equal to 1. just based on our zero exponent rule. So what if instead of calling this 5 times 1, we called it 5 times x to the 0 power, or simply 5x to the 0 power? Right? We don't have to show the dot here. We have implied multiplication. Well, technically, this is still 5 times 1, since x to the 0 power is 1, and 5 times 1 is 5. So this is one reason why we can call 5 having a degree of 0. Because we can always multiply in x to the 0 power and it doesn't change the value, since x to the 0 power is the same as 1. Okay, but there's some other consideration that we need to think about when we're trying to classify whether an expression or a term is a polynomial. And what we should say is that polynomials cannot have negative exponents or fraction exponents on the variable terms. So some examples of polynomials, or in this case monomials, would be things like the number 17, or 5y to the 3rd power, or 7p to the 5th power. Those would all be monomials, or a small polynomial. But these are examples of not polynomials. Polynomials. So if you have something like 3 times the square root of x, or x to the 1/2 power, or x to the -3 power, or even something like 2 over x, where you have a variable in the denominator of some fraction. Because remember, based on our negative exponent rule, this would be the same thing as 2 times x to the -1. So sort of hidden in plain sight, this expression, if we use our negative exponent rule, is the same as 2 to the -1. So this cannot be a polynomial. So you can't have variables in the bottom either. Okay, so far we've really just looked at monomials, but we can think of polynomials as being just monomials that are added or subtracted to each other. So you can think about this like, imagine that we had 4x to the 7th power, and I added that to 3x to the 2nd power. Well, then this whole thing is a polynomial with 2 monomial terms. And specifically, we call a polynomial with two terms binomials. But the key thing here is that a polynomial is going to be made up of a bunch of monomials that are added to each other. Okay, and you can count the number of terms here, 1, 2, because they're separated by addition and subtraction. So as soon as you have this addition sign, you know that this is a term and this is a term. Let's look at another example here. Let's look at x squared plus 5x minus 8. Well, again, we have 3 terms here, 3 monomial terms, but this whole thing is a polynomial. And this is a polynomial with 3 monomial terms. And specifically, we're going to call these trinomials because there are 3 terms. We don't have special names for any polynomial that has more than 3 terms. We just call them polynomials at that point. So if you had something like 3x to the 4th plus 5x to the 3rd minus 10x to the 2nd plus 9x minus 100. Well, I have 1, 2, 3, 4, 5 terms here. So we would just call this a 5-term polynomial. Mathematicians start out with a lot of energy, right? Naming these things. But then once we get to 4, we just say, you know, screw it, we'll call them all polynomials. Okay. But now, when we think about the idea of degree, we said that the degree of a monomial is the exponent on that monomial, right? But if we have a polynomial with many terms, we need to think about what is the degree of this polynomial, right? Because we have a lot of exponents to choose from. So the degree of a polynomial with many terms is simply the highest exponent on a variable term. Okay, so in this example, we would have a 5-term polynomial of degree 4, since this is the highest exponent. And then another bit of terminology is that for each term, the number in front of the variable which is being multiplied by the variable is called the coefficient. Okay, so if we look at this 5-term polynomial, we can say that this term, the x to the 4th power term, has 3 as its coefficient. And this term here, 5x to the 3rd power, has a coefficient of 5. Right? So the number that's in front of the variable is called the coefficient. And what we call the leading coefficient is the coefficient on the monomial term with the highest degree or exponent. So for this polynomial here that we were looking at, the highest exponent, we would call this x to the 4th the leading term, and the leading coefficient is going to be 3. Okay. And you're going to have a lot of questions in Hawks, well, actually not that many, but that ask you to classify the polynomial and then determine its degree and determine the leading coefficient. So let's look at some examples of that. Okay, so we're going to determine the degree and leading coefficient of the given polynomial. Okay. Okay, so in this example, we have 3/4 times x to the 4th power minus 2, I used y here. Let me go ahead and change this to be consistent. Let's make them all y's. Okay, let's call this 3/4 y to the 4th power minus 2y to the 3rd power plus 4y minus 6. So right off the bat, can anybody tell me how many terms there are for this polynomial?
Four?
Yeah, because again, when we're trying to determine how many terms are in this polynomial, you just have to ask yourself how many like addition and subtraction signs are there. So like this is going to be a term, this is going to be a term, this is going to be a term, and this is going to be a term, right? The terms are separated by the addition and subtraction symbols. Okay. But the question here is really asking, it's good that we know that this is 4 terms. That's going to be a useful skill for solving all kinds of problems in college algebra when you guys get there. But now we really want to just determine the degree and the leading coefficient. So what would be the degree of this 4-term polynomial?
4?
Yeah, we would just say that the degree of this polynomial is 4. So that means that this guy, this term right here, is our leading term. Okay, and the number that's being multiplied by it, so we can call the leading term is the whole thing 3/4 y to the 4th power. But the leading coefficient is just the number that's being multiplied in the front, 3/4. So a lot of the problems in Hawks are going to be like this, where they just give you a polynomial and they ask you to break the polynomial down term by term. And they'll ask you, what is the coefficient? You know, is it a variable term or is it a constant term? Okay. So if it's a variable term, they'll ask you what the coefficient is. And they might ask you what the degree is. If it's a constant term, then there is not going to be a degree, or you would say its degree is 0, so it's not a variable term. So again, when you just have a plain number that doesn't have a variable on it, we call these things constants. Because the variables are like placeholders for a number that we could plug in later, but the number itself that doesn't have a variable next to it, well, that's just going to stay the same, or it remains constant. Okay. So let's look at this one. And we have 4z to the 3rd power minus 7.5 z to the 2nd power minus 5z. Okay. So what is the degree of this polynomial?
3.
Yeah, it's just 3. And what is the leading term?
7.5.
Okay, so that is definitely a good try. But remember, the leading term has to do with the monomial term that has the highest exponent. So once you've identified this as the highest exponent term, then that's the only thing that you're focused on, right? Leading term doesn't mean the biggest number, because certainly in this example, we had 3/4 is smaller than 4, right? But the leading term is the one with the highest exponent. So we're just going to say that 4z to the 3rd power is our leading term. And that must mean that the leading coefficient, the number in front of that term, is just 4. Does that make sense? Okay. You're going to be asked to simplify polynomials. So let's talk about that. Simplifying polynomials. So simplify in this context is just going to mean combine like terms, which is something that we've already been doing. Okay, so I'm just going to jump in with some practice problems and see if we can simplify these. So let's say that we're given the polynomial 5x to the 3rd power plus 7x to the 3rd power. Can anybody jump in and tell me how I would simplify this, or how I would go about combining like terms? What should I simplify this down to?
You multiply, I'm sorry, you add the whole numbers and the exponents.
So you're not going to do anything with the exponents here, but you're on the right track. Remember, when we combine like terms, we need to think about this as apples and oranges, right? And so you can think about this expression here, this term, as being 5 apples, right? We're just going to call x to the third power some object 5 apples. And if I add 7 apples, well, how many apples do I have in total?
12.
Yeah, so I'm just going to have 12 x to the third power. So that's going to be a caution, right? Last time we said that if we had 5 x to the third power times 7x to the third power, that when you're multiplying these two terms, you should get 35x to the, and then you add the exponents to get 6. But that's not the same as 5x to the third power plus 7x to the third power, where we found that this one came out to 12x to the third. Right, so when you add polynomials or when you simplify or combine like terms, the exponent doesn't change. So it doesn't change when you add or subtract. And we might not have thought about it too deeply before, but when we say combine like terms, we mean specifically add or subtract like terms. Okay, so you're going to want to be careful not to do anything with these exponents. We're just going to say I have 5 apples. When you're adding, when you're simplifying, we have 5 apples and we're adding that to 7 apples, so we should have a total of 12 apples. And I know it's super silly, but using that analogy of using apples, it really will help you, prevent you from making mistakes. Okay, let's look at another one. Six x to the third power plus 4x to the third power minus 2x. And again, we want to simplify this expression, but you want to take care to only combine like terms. So can anybody venture a guess as to what this would simplify down to?
X to the third power minus 2x?
Yeah, exactly. So these guys are like terms because we have x to the third power. So if you have 6 of these things and you add 4 of the same thing, then you should get 10 of those things. And because this is different, it's not a like term, we're just going to have to leave that alone. We can't combine them because it's apples and oranges. So this would be simplified. Does that make sense? Okay, let's look at some more examples. Maybe we have 1/2 y plus 3y minus 2/3 y squared. Okay. Well, we want to simplify this, but here we have these as like terms. So what I like to do is circle the terms that are like terms, and then go about combining them. So I have half of this object that I call y. So you could say I have half an apple, and I'm adding it to 3 apples. So I should have 3.5 apples. But that would be nice if we could just call, 1/2 plus 3 is equal to 3.5, or you could call that 3.5. But we really want to keep everything as a fraction. This would be nice. But what we're going to do instead is call this 1/2 of this object y plus 3/1 y. And you might notice that I left a little bit of space here because I need to, in order to add these two terms together, I need to get a common denominator for that fraction. So I'll multiply in 2 times 2, or 2/2 for this fraction so that I get 6/2. And now we have a common denominator. And I know that I'm bringing down the y's here, but really we're just working with the coefficients, the numbers in front. So when you add these two numbers together, you're going to keep the common denominator, and you're going to add the numerators. So this should be now 7/2 y. And since this guy is a different term, it has a different exponent, that will be minus 2/3 y squared. And so this would be simplified. So that was just an example to sort of, throw a shock to the system, give you some fractions, because they're definitely not going away. I don't know. I always say that fractions never go away, and it's true, but students tend to let their guard down, so I like to throw some of those at you. Let's take a look at the next problem. Okay. So, can anybody tell me what this would simplify down to?
We simplify both y4 and y2. Divide. No, not divide. Yeah, 2 and 2.
Yeah, so what we can do is, I'm just going to underline these because they're like terms. And if we're going to combine these like terms, remember, combining like terms just means adding or subtracting these guys together. So 7 minus 3, you can think of that as 4. So this will be 4y to the 4th. And then we have these y to the 2nd powers. So this is just 2 plus 10, which will be positive 12y to the 2nd power. Any questions about that one? Okay, well, you have a couple of questions in the homework that talk about polynomial functions. Evaluating polynomial functions. And so this is sort of like a convenient way, this idea of function. When we use the word function in our everyday life, we just think about things working, right? Like something is functional, that means it works to perform some sort of operation. Like a sweater is functional in cold weather because it performs the operation of keeping you warm, right? It does some work. But a function in mathematics has a very specific meaning. And we think about functions as being an expression with variables that takes an input value and then can be solved or simplified to get some output value. Okay. Now I know that sounds like a technical definition, but really we can think of these polynomial functions. They are written typically like this: p of x is equal to, let's say, I'm just going to put here polynomial here. Okay, so when you see this p of x, a lot of times students will think that you're multiplying p times x, but this is just the function name. And because we're working with polynomials, we're just going to call them p for now, but the function name could be anything. In college algebra, we use f for a function's name. The x here is going to be the input value. So they're going to give you a number here that you're going to plug into the equation, and this is usually the polynomial expression over here. So you're going to plug the x value into the polynomial expression and simplify it. So let's look at an example of a polynomial function. So here's an example. P of x is equal to x squared minus 4x plus 13. And they'll ask you something like, find P of 3. And that's all they'll ask. Well, what they're telling you to do here is they're saying, take the number 3 and substitute into the polynomial for x, and then simplify. So what we could say is that P of 3 is equal to 3 squared minus 4 times 3 plus 13. And then that simplifies down, and you could throw this into the calculator, right? This would be 9 minus 12 plus 13. So you should get 10 when you solve that. Okay, so let's look at some more of these polynomial functions, just to see, you know, what we're going to be expected to do in the homework. So let's do this. Practice with polynomial functions. 1. Given p of x is equal to 4x squared plus 5x minus 15, find p of negative 2. Okay. Well, this is primarily what they're asking you to do. Again, they're saying plug negative 2 in for the x in this expression, and then simplify the expression. So you could say, you know, p of negative 2 is equal to 4 times some number squared plus 5 times some number minus 15. Right? And I'm putting parentheses wherever I'm going to plug in this value of negative 2. So I'll go ahead and put negative 2 here, negative 2 here. And now we're not concerned about the left-hand side of this expression. We just need to simplify the right-hand side, the part that we plug the number into. So we're going to use our order of operations to slowly simplify this side of the expression. So negative 2 times negative 2 is going to be positive 4. So we'll have 4. This 4 just comes down, but this exponent will be 4 plus, well, 5 times negative 2 is going to be negative 10 minus 15. And if we continue simplifying, we should get 16 minus 10 minus 15. And then 16 minus 10 should be 6 minus 15. And then finally, we should have 6 minus 15 would be negative 9. And that'll be your answer. Okay, let's look at another example. So given p of y is equal to 5y to the third power plus y to the second power minus 3y plus 8, find p of 0. Okay, now I'm going to give you guys a little bit of time to write that down. Again, we'll start off by writing p of 0, understanding that 0 is the input value, and we need to plug that in for the variable. So this function has a variable of y, and we're replacing all of the y's with this number 0. So I'm going to go ahead and write this expression, but I'm going to put parentheses everywhere I have a variable. So 5 times y to the third power plus y to the second power minus 3y plus 8. So be very careful. The number here only gets plugged in to the terms that have a variable. Again, that's why we called this a constant term, because it does not change, right? Only the variables will change. That's why we call them variables, okay? So we're going to plug 0 into this expression and then simplify it. Well, this is a really nice one because 0 to the third power is 0. 0 to the second power is 0. So really this is 5 times 0, 0, and then 3 times 0. So you could say that this is 5 times 0 plus 0 minus 0 plus 8. And so everything here that's a 0 sort of cancels out. And you're just left with positive 8. Okay, but there's one more complicated version of this problem that you will see in in Hawks, but it's not that complicated. I'm just being a little bit dramatic. So let's look at that example. Let's say that they give you, so given the polynomial function 6x plus 13. They'll say find p of 2a plus 1. Okay, so before we were just plugging in a number in for the x. But it looks like this polynomial expression, 2a plus 1, right, that's a binomial. This is a binomial input because there are two terms here. So we don't just plug in a single number in for the variable. What we're going to do is we're going to plug this expression in for the x. And since there's more than one term, when we plug it in, we're going to want to plug it in with parentheses. So what we'll say is that p of 2a plus 1 is equal to, and then it's 6 times something plus 13. And the input value, or the input expression, will get copied right here next to the 6 because it's 6x. So I'm going to put 2a plus 1. Well, now, again, I don't really look at this left-hand side. I'm just focused on simplifying this right-hand side of the expression. And to me, if I see 6 on the outside of this parentheses, I'm sort of tempted to distribute. So that's the first thing you're going to want to do. You're going to want to distribute the 6 and multiply it by these terms. So we'll get 12a plus 6. And then we can just bring the 13 down. Remember, once you distribute, you don't need the parentheses anymore. But now we want to simplify this expression, and we can combine this term and this term. So our final answer should be 12a, and then 6 plus 13 should be 19. Okay, so this was an example where, the input value is not a single term. It might be a polynomial expression itself, but the principle is the same. You're going to take that polynomial expression, plug it into the variable, and then you're going to simplify that expression. Okay. So that would be basically the gist of what section 12.4 is all about. There aren't that many homework problems. I think there are 10 problems in that section, but get in and make sure that you practice that one. We're moving on to section 12.5 now. And section 12.5 is all about adding and subtracting polynomials. Okay, and the reason why it seems we're like just bulldozing through these sections is because, again, you've seen these ideas before. We just were calling them by a different name. Okay, addition with polynomials is really straightforward. So if only I could spell polynomials, addition with polynomials. This is all you're going to do. You're just going to combine like terms. So if you're given two polynomials and you're told to add them together, you are just going to combine like terms. So let's get some practice problems in. Let's say that I had the polynomial x to the third power plus 2x squared minus 4x. And then I added that to 5x to the third power minus 10x squared. So I want to be clear here a little bit. You know, this has 1, 2, 3 terms. So we might call this a trinomial. And we're adding that to something that has 2 terms, a binomial. Well, when you need to add a trinomial to a binomial, you're just going to combine like terms. So you can just ignore the parentheses for these kinds of problems and then just look at your like terms. We have x to the third power here, and we need to add that to 5x to the third power. Okay, so that'll be, we have 1 apple and we're adding that to 5 apples, so that would be 6 apples. Okay, that takes care of these guys. Now we can move on to our x to the second power. We have 2x to the second power here, and then we're going to add that to negative 10x to the second power, so plus negative 10x to the second power. Well, 2 plus negative 10 should give us negative 8x to the second power. So that takes care of these guys. And then we just have negative 4x left over. So what we're going to do is just write our answer in what we call standard form. So you want to write it with the highest exponent first, so we can just write our simplification as 6x to the third power minus 8x squared minus 4x. And you're done. You've added these two polynomials. Okay, you don't have to organize it the way that I organized it, but I'm just trying to demonstrate that all we were doing is looking at the x to the third powers, x to the second powers, and just combining like terms. Let's do another example. So we want to add maybe negative 3x to the fifth power minus 5x to the second power plus 14, and then add that to negative 8x to the second power plus 7x minus 4. Okay, so in this problem, let me go ahead and sort of write a line here just to separate it from the problem above it. In this problem, we have 1, 2, 3 terms, so this is a trinomial being added to another 1, 2, 3, another trinomial. And we're just going to start off by combining like terms. I mean, that's all there is to it. So we might just scan the polynomials to say that I only have a negative 3x to the fifth power, right? There's not another x to the fifth power, so I'm just going to write that one down. Then I might say, okay, I have x to the second power. Let me see if I have another x to the second power. So negative 5 plus negative 8 should be negative 13x to the second power. Since we're at the second power, I'm going to go down to x looks like we just have this one x term. So I'm just going to bring that down because there's nothing to combine there. This guy doesn't have an x term. So we have 7x. And then finally, we can look at the constant terms. I'll go ahead and use a different shape like a square. We have 14 minus 4, which should be positive 10. So that's going to be your answer. Were there any questions about this one? Okay, let's do some more addition. There's all kinds of ways to organize your scratch work if you need to. So I usually work my problems out the way we did that last problem, where I don't really write a whole lot. I just sort of circle the like terms or use different shapes. So I use like circles, squares, triangles, or underlines. But you could use different colors to box in the like terms. That's another strategy that's very useful. Some people like a stacking method. So I'm going to show you this stacking method for this problem. So we have the polynomial x to the third minus x squared plus 5x. And then we're going to add this trinomial to a polynomial of 4 terms. We have 4x to the third plus 5x squared minus 8x plus 9. Again, this is a trinomial. And we're adding that to 1, 2, 3, 4, a polynomial with 4 terms. Again, we don't have a special name for that. So some students like this stacking method. And it's sort of like adding big numbers, like 123 plus 247. You would stack the terms or stack the place values. So what we're going to do here is instead stack these terms with a common or like variable. So we have x to the third minus x squared plus 5x. Okay, that's the first polynomial. Then you can stack this underneath it, and since we're just adding, we're going to add 4x to the third power plus 5x to the second power minus 8x and then plus 9. Now I'm putting the plus 9 over here with nothing above it because this first polynomial didn't have a constant term. But you notice that we've lined up our like terms. So we can just say, okay, if I have one of these guys and then I add 4 of them, I should have 5 of these guys left over. And if I have -1 of these guys and add 5 of them, then I should have positive 4 x squared terms, right? And then if I have 5 minus 8 of these terms, then that should be -3x. And then we can just bring the 9 down. And this will be your answer. Does that make sense? Okay. Do you guys want another example of adding polynomials, or does that seem like a pretty simple enough process that the 3 examples are sufficient? I'm going to take that as a yes. All right, let's jump into subtracting polynomials then. So the process for subtracting polynomials is also relatively simple. You're not going to be changing the exponents on any of these problems. But there is a slight complication with subtracting polynomials. So what I would say is that when you subtract polynomials, what that really means is you're going to distribute a negative sign or distribute a -1. That's going to be the first step. And then the second step will just be to combine like terms. So a little bit more complicated than adding, but fundamentally all you're doing is combining like terms. So this will make more sense if we jump in with some practice. So let me throw this problem at you. We have 5x squared minus 3x minus 7. And then from this trinomial, we're going to subtract 2x squared plus 5x minus 8. Okay. So don't get bogged down with all of these subtraction signs and all of these addition signs, right? Fundamentally, what you're looking at is this guy in parentheses, which is a trinomial. And we're subtracting 1, 2, 3, another trinomial. But what we want to do is we're going to use this negative sign and distribute it as though it's a -1. So this is like multiplying each term. So if this negative sign, if this minus sign is in front of the parentheses, then that's the same thing as having a -1. We're going to multiply each term by -1. And once we do that, we can just drop the parentheses entirely. So if I have -1 times this term, I should have -2x squared. -1 times this term would be -5x. And then a negative times a negative will be +8. Then I can drop all of the parentheses entirely and just bring down this first trinomial. So 5x squared minus 3x minus 7. And now it's just a matter of combining like terms. So if you guys like the stacked method, we can stack these terms now. We can have 5x squared minus 3x minus 7. That's the first polynomial. And then we're just going to stack these terms. So we'll have minus 2x squared minus 5x plus 8. Well, 5 minus 2 is 3x squared. -3 minus 5 should be -8x. And then -7 plus 8 should be +1. So that's your answer. Again, just to recap, the only difference for subtracting polynomials is that you're going to distribute that negative sign. You're going to distribute it like it's a -1. Multiply it by each of the terms in the parentheses that follows the negative sign. Then you can write down all of your terms, you can stack them, and then just combine like terms. Okay, let's do another example. 9x to the fourth power minus 22x to the third power plus 3x to the second power plus 10 minus 5x to the fourth power minus 2x to the third power minus 5x squared plus x. Okay, so like I said, there's only two steps fundamentally to this problem. We can just leave the first polynomial. We have 1, 2, 3 terms. I'm sorry, 1, 2, 3, 4 terms. And we can just leave this one alone. We can drop the parentheses because there's not a negative sign in front of the parentheses. So there's nothing to distribute here. Now we can just say that this is 9x to the fourth minus 22x to the third plus 3x squared plus 10. But for that second set of parentheses, we're going to want to distribute this like it's a -1. And so this is going to multiply or change all of these to their opposite signs. You can think about it that way. Multiply by -1. So we should be getting -5x to the fourth, positive 2x to the third, positive 5x squared, and negative x once you distribute that negative sign. Okay, there's a lot going on here, so I think that stacking and combining like terms is going to be a really useful strategy. So I'm just going to rewrite this as 9x to the fourth minus 22x to the third plus 3x squared plus 10. And really, a lot of times what I like to do is put the 10 all the way at the end. And you'll see why in a second. And it's because when I stack this polynomial underneath their like terms, so -5x to the fourth plus 2x to the third plus 5x to the second, well, I'm going to put minus x right here because I sort of want to keep these in order, right? I want x to the fourth, x to the third, x to the second, x, and then my constant term. So in some sense, these terms with their different degrees, they're like place values, and you sort of want to line your place values up. But in any case, we're just going to go ahead and combine these like terms. So 9 minus 5 is going to be 4x to the fourth. -22 plus 2 will be -20x to the third. 3 plus 5 should be positive 8x squared. Since there's no x term in that first polynomial, I'll just bring negative x down. And since there's no constant in the second polynomial, I'll just bring the 10 down. And so this will be your final answer. Does anybody have any questions about this problem? All right, cool. Let's do one more. Eight x to the third plus 5x squared minus 14 minus -2x to the third plus x squared plus 6x. Okay, let's just begin. So what I would do is just bring down the first polynomial exactly as it is. We haven't changed it. The only difference is that we left the parentheses off. And then what we need to do is just go ahead and distribute this negative sign as though we're multiplying a -1. So we should be getting a positive 2x to the third, a negative x squared, and then a negative 6x. Then we can go ahead and stack this. If you prefer the stacking method, I'm just being consistent now. I usually don't stack them myself. I'll just go ahead and circle the like terms. But since I've already started, let me go ahead and finish. Then we're going to stack this guy, 2x to the third minus x squared minus 6x. Oh, there we go. Let me go ahead and move this minus 6x. Okay, so I wasn't paying attention to how I put these in order. You'll notice that I'm going to put the 6x before the 14 when I have my final answer. But in any case, we are going to stack the like terms and then combine them. So this is 8 plus 2, which is going to be 10x to the third. This is 5 minus 1, right? Because we have 5 apples here and we're taking away one of the apples. So we should have 4 apples left. And then here's where I said I sort of wrote this in the wrong order. I like to have this as x to the third, x to the second, x, and then the constant term. But that's not a big problem. I'm just going to put negative 6x here first and then minus 14. Technically, since we're just adding and subtracting, the order doesn't matter, but the order of x to the third plus x to the second plus x plus whatever the number is tradition. So most instructors, most mathematicians will write it in this way, even though when we add and subtract, the order doesn't really matter as long as these signs are correct. So we call this standard form. Standard form is when the polynomial is listed in descending order with respect to the exponents. Okay, and that's just a note. That's it's not a super big problem or anything. You know, Hawks will take it in whatever order, but I would just say try to keep it in standard form, in descending order of exponents. But otherwise, that's basically it for adding and subtracting polynomials. Did anybody have any questions about those two processes?
Will we see fractions as well?
Yeah, you might see some fractions in the homework. All the example problems that I have here are whole numbers. Let's see. Yeah, do you want to see one with fractions?
Yes, please.
Okay. Let's do this. So subtract. Let's do 3x to the fourth minus 2/3 x to the fifth plus 10 minus 2 over 7 x to the 5th plus 1/2 x to the 4th minus 5, 9 x. Okay. Just made that one up on the fly. So the strategy here is going to be the same. We're subtracting these two polynomials. They're both trinomials. The only complication is that we have some fractions in the mix. Okay, so the first thing you're still going to want to do is go ahead and distribute this negative sign. So this negative sign, when you distribute it, you're going to multiply each of these terms by a -1. And really, you're just multiplying the coefficient by a -1. So really, this will become -2 over 7 x to the 5th. This will become -1/2 x to the 4th. And then negative times a negative is going to be positive 5/9 x. Okay. And you only have to worry about common denominators when you add fractions, add or subtract fractions. So what we have to do is write this polynomial down as it is. And then here, my strategy would be to take a look at, like the first way that I showed you guys. We'll look at the x to the 5th power first, even though I didn't put it in the correct order. Hawks may not put them in the correct order. So let's take a look at the x to the 5th power first. What I'll do is say that this is x to the 5th power, but I'm really just going to focus on the coefficients here. What I want to add is -2/3, or what I want to subtract, right, is -2/3 minus 2 over 7 here, right? Because those are the coefficients that belong to x to the 5th. So I need to get common denominators before I can add these. So you'll have to find the LCD. The LCD in this case is going to be 21. Okay, so this will be like multiply that by 7 over 7 here so that you get 14. But don't forget the negative sign. And then we'll multiply this one by 3 over 3 so that we should get 6. Does anybody have any questions about this process here? I didn't really explain a whole lot of how I knew the LCD would be the 21, but it's essentially because the original denominators here, when you multiply them, you get 21. Then we can go ahead and subtract these numbers, and we should get -20 over 21. And unfortunately, that doesn't simplify. So the term we're really going to be looking at is this times x to the 5th power. Well, that takes care of my x to the 5th powers. Now I need to move on to the x to the 4th powers. So I'll go ahead and box these in just so I don't mix them up. And I'm going to be thinking about x to the 4th power, but I'm just going to be working with the numbers in front. This is going to be 3 minus 1/2. But really, we want to write this as 3 over 1 minus 1/2. And then we want to get a common denominator. So I'm just going to multiply this fraction by 2 over 2 to get 6 over 2 minus 1/2, which at the end of that deal, we should get 5 over 2 x to the 4th. Luckily, this is the only x term, and this is the only constant term. So that's pretty much all the work I have to do here. And let me put it all back together. We should have negative 20 over 21 x to the 5th power comes first. Then this is a positive 5 over 2. So I'm going to put plus 5 over 2 x to the 4th. And then I'm going to put plus 5 over 9 x plus 10. And that is going to be your answer. I cannot combine any of these terms, so I'm just going to leave it as it is.
Thank you.
Yeah. My pleasure. Well, even though that last problem we just worked on was a little bit complicated because of all the fractions, I know they're deeply frustrating for you guys. They are for me too, but we just sort of have to grin and bear it. Hopefully, most of the problems in your Hawks homework will be whole numbers, but that's all the material for tonight. Again, the reason why we're getting out a little bit early is because these two sections, we've already been dealing with the fundamental concepts. We've just been calling them something different. So now we're calling them polynomials. And instead of saying we're combining like terms, we're saying adding polynomials. And when we subtract polynomials, we're distributing and then combining like terms. Again, not new ideas at this point. So just get into the homework, work on these two sections. These two sections have now opened up. Their due date is going to be for Sunday at midnight. So just make sure you get practice, and if you get stuck on something, just make sure that you reach out for help. As always, you're able to message me in Remind, message me in Canvas, come visit me or the other tutors in Math World, but otherwise, if you guys don't have any questions, you're free to go. Have a good night.
Good night.
Thank you.